Hello and welcome to this video. In this video we are going to look at how to use the Lorentz force to explain the principle of induced voltages. This is in the context of generating electricity from energy of motion. So let's see how this can be described. In the past videos, I have talked a lot about Faraday's law of induction, and here you can see it again. So Faraday's law of induction summarizes two types of induction: the induction of motion and the induction without motion. For the case of induction with motion, we can have a changing surface here, and then this flux integral will change. Or also we can have a movement of the surface in the magnetic field. For the induction without motion, this magnetic field here can be changing and the surface stays exactly the same. In both cases, we observe a change in the magnetic flux with time, and this results in an induced voltage Ui. We have also seen in the past videos already that there is a magnetic field, of course, necessary in order to obtain induction, and that this magnetic field might be generated with a permanent magnet or with an electromagnet. So after this recap, let's now look at it a bit differently. And that is, let's look at the Lorentz force. So if we look at the force on a charge Q, we see that this force is caused by the electric field and also by the magnetic field if we have motion. And this combined force on the charge Q is called the Lorentz force, or sometimes also only this back part here is called the Lorentz force. But let's talk about this combined force on charges. So if we consider that we have an electric field, as shown here, going from top to bottom, and we have a positive charge, but we don't have any magnetic field, then this means that a positive charge will experience a force in the downwards direction, in the same direction that the electric field is pointing. And this can be seen from the equation up here. So if we have an electric field vector, the charge Q is just a scalar, we multiply it, then we get a force vector that is in the same direction as the electric field vector. So charges in electric fields experience forces. If we have a negative charge, we will also observe a force, and this negative charge will observe a force in the opposite direction. So if the electric field is pointing from up to down, then the force of the negative charge will be going upwards. And this can be seen from this equation by, if you put in here for the Q a negative charge, so with a minus sign, then we will have a force that opposes in direction the electric field vector. So negative charges in an electric field move upwards, positive charges in this electric field move downwards. Now let's consider that we turn on a magnetic field. And here I'm using the magnetic field representation, again, such that the magnetic field is shown by the small crosses you see here. So if we see the cross, it's like the back of a dart arrow. That means we have into the plane here a magnetic field. We have all these crosses here show that we have a homogeneous field because the crosses all have the same distance. So we have a homogeneous field into the plane of the screen here. Okay, so let's consider the positive charge here, and it's moving in this direction. We have a magnetic field that's pointing backwards, and that means the cross product of the vectors results in an upwards force. So this cross product here means that if we form the cross product, we have the direction that is given by the right-hand rule for the resulting force vector, and in this case that means that a positive charge will experience an upward movement. So if this charge then is moving in this direction and it has an upward movement, it means it will be moving upwards. So it will not move along a straight line, but if a charge is moving in the electric field, it will be moving upwards as shown here for the positive charge. Let's look at the negative charge next. So if we have a negative charge, again, we have to consider here the negative sign, and that means that the force vector is showing in the opposite direction. Or if we have now a negative charge moving in this direction, the negative charge is deflected downwards by the magnetic field. So charges moving in a magnetic field experience a force, and the negative charge here is going downwards, the positive charge would be going upwards. And all of this is summarized here in this force vector of the Lorentz force, where we have the electric field effect and we have the magnetic field effect included. So what does this have to do with induction? Let's go one step further and let's now consider that we have a conductor, and this is our conductor here, and this conductor, it could be a piece of wire, for example, this conductor is moving in a magnetic field. So the whole conductor is moving in the magnetic field in this direction. Again then, the charges in the conductor here will experience the Lorentz force. And that means that the negative charges will experience a force downwards. If there are available positive charges that can move, then also positive charges would move upwards. So if this was a piece of semiconductor where we have electrons and holes that can move, then we would have holes accumulating at the top. We would have electrons accumulating at the bottom. If this is just a piece of metal where only electrons can move while the positive charges are fixed in space, that would mean the electrons are moving downward and the positively charged atoms remain at the position they are at. So if we have this conductor moving in a magnetic field, we get a charge separation, as you can see here. And such a charge separation is the same as saying if I pull the positive charges upwards, the negative charges are downwards. That's the same as having a voltage, so an induced voltage. So we have a voltage between the top side and the bottom side. We can also show this in terms of the electric field. So the electric field goes from the positive charges to the negative charges. That means we have an electric field vector pointing downwards here. So for a conductor moving in a magnetic field, we will obtain an electric field between the top side and the bottom side. And this electric field between top side and bottom side means we have a voltage, and the voltage can be calculated in equilibrium. So if nothing is changing, we can calculate the voltage by noting that the voltage is given by the integral of the electric field over the length L of the conductor. So we take the line integral of the electric field from the top side to the bottom side, and that will then give us the induced voltage between the two sides of the conductor. And therefore, also the Lorentz force can be used to explain that if we have this moving conductor, we will get an induced voltage. And now, of course, kind of conductor wires rolling in a magnetic field, that is not that practical. But if you think of wire loops spinning in a magnetic field, then we are again back at the generator principle. And that means we can also use the Lorentz force to explain that if we have a wire spinning in a wire loop spinning in a magnetic field, we will get an induced voltage. And this voltage then is used for getting electricity out of our generator. So summing up this with the equations, that means we have, first of all, this Lorentz force approach here that gives us an induced voltage, calculating by integrating the electric field that is obtained when charges are separated in the magnetic field due to the Lorentz force. Alternatively, we have seen previously, we can use Faraday's law of induction to also calculate the induced voltage. And here we have to look at the time derivative, that is the change of the magnetic flux with time, and the magnetic flux is given in the integral down here, so you obtain it by integrating the magnetic flux density over the area of the loop that you have, for example, in your moving in your magnetic field. So both of these principles can be used in order to calculate the electromotive force. And actually the two are not really a different theory as you first might think, because they look quite different here, but they can be traced back to the same unified theory, and that's based on Maxwell's equations. So you can convert one to the other, and also other way around, by using the law and Maxwell's equations. You can derive the opposite or the other of these equations. So even though these equations look different, they are part of the same unified theory, and then it depends on your exact geometry that you want to calculate if it's easier to use this relation based on the Lorentz force, or if it's easier to use Faraday's law of induction. Typically, the basis for calculations is Faraday's law of induction, as this includes all the cases, as we have seen at the beginning. So normally we will start here, but the two are related, as I've shown you in this video. Thanks for watching.